Good morning, good afternoon, good evening. No matter when you are, it's another exciting episode of 7th grade science live from the Brenna bunker in the quarantined Southeast United States. This is Ace Academy 7th grade science. So once again, we are still recovering from a week off for spring break, but I'm hoping you guys are starting to get back into the swing of things. And so as we do, we're going to hit day 2 here. So 7.E.1.1, as you can see on our screen of our Earth system, day 2 says I can describe the properties of the Earth's atmosphere. Now, the couple of things we're going to run into. Number one, we're going to describe when we talk about properties such as what? Air pressure, that would be one. Temperature, that would be another. Altitude above the ground would be a third. So when we talk about properties, think about how cold is it? What's the air pressure like? And how far off the ground are we? So as we scroll down here in our set of notes, it says, I can describe again the properties of the Earth's atmosphere. The atmosphere is divided into layers based on observed properties, divided into 5 layers. So how many layers, guys? 5 layers. Okay, so let's get into the layers here. So right here, this little graphic's kind of got the entire thing laid out over here, and then they blew up this chunk right here down here because it's everything's kind of compressed down at the bottom. So the lowest layer is where all the weather happens. It's called the troposphere. Right there's the name of it, troposphere. The troposphere is a layer exists from the sea level to a varying distance above the Earth. It depends on where you are. At the pole, it's the closest to the ground that layer, the top of the layer is, and at the equator, it's the highest. But on average, it's about 10 kilometers. So when you guys talk about the troposphere, when we say, hey, what's the top of the troposphere altitude-wise, you're going to say 10 kilometers. Or if you look at this map, it's about 6 miles. But we're going to try to keep things in metric here, so we're going to say 10 kilometers. So the troposphere is the smallest in height of the layers of the atmosphere. From top to bottom, it's the shortest. But it contains most of the water vapor and 75% of the gas molecules that make up the entire atmosphere. So in the smallest layer, you have the most stuff. But again, it's the closest to the surface of the Earth where the gravity is, so that kind of makes sense. So it is where all the weather occurs except for the tops of the tallest and most severe thunderstorms. You can see a picture of a thunderstorm right there. Thunderstorm builds up, and sometimes the tops of those thunderstorms kick up into the next level. That kind of reminds me, it's like, hey, wait a minute. Oh, no, don't do that. Sometimes thunderstorms, again, so 10 kilometers, 6 miles, it's about, 32, 34, 35,000 feet. Sometimes you can get those thunderstorms that stick way up into the atmosphere. And what you end up seeing is something that looks like this. Now, well, that's a really poor picture of one, but when you see that flattened out top of it like that, they call it the anvil. And when you see it, here's another one from space, big, huge thunderstorm, but here's flattened out top. So when the storm gets so tall that the top of it runs into literally the jet stream, it starts knocking the top of it off like that. And they call that, it's called the anvil. So it gets up so high up into the stratosphere, which is the next layer up, that it literally sticks up into the jet stream. So the storms can hit almost 60,000 feet in altitude. And that seems to be all right, there we go. So again, there's that anvil where that thing is run up, and the top and the jet stream winds are literally knocking the top of it, and smashing the top of it over because of the wind way, way, way up in the atmosphere. So 60,000 feet and change are the tallest storms, but that only occurs way out west in the Midwest, where what they typically call it Tornado Alley. Missouri, Arkansas, North Texas, Oklahoma, where all those storm chasers are out there chasing tornadoes. That's where those monster tall thunderstorms get. Around here on the East Coast, we rarely see storms above 30, 35,000 feet. You get a 35,000 footer here on the East Coast. That's a big deal. Um, so only the tallest thunderstorms crack into the next layer. But other than that, all the weather happens down here in the troposphere. So air pressure is greatest at the surface of the Earth. Well, duh, right? Because again, air pressure is the result of gravity acting on all the molecules of gas in a column above, where you're testing the air pressure. And it decreases as you go up in altitude. In the troposphere, temperature declines as you go higher by an average of 6.5 degrees Celsius for every kilometer you go up. The top boundary of the troposphere is called the tropopause. So here's a word you need to kind of know, the tropopause. So the tropopause is what? It's the top boundary of the troposphere. The troposphere is what? It is the lowest level of the atmosphere here on Earth, where all the weather occurs, and 75% of the gas molecules that make up the entire atmosphere happen to live there. That is this level right here, down here at the very bottom from where it says 10, from ground level to 10 kilometers. The next layer up is called the stratosphere. It is from the tropopause, which is the top of, there's that word again, tropopause at the top of the troposphere, at approximately 10 kilometers to approximately 50 kilometers where we hit the stratopause. Oh, look at that. It seems to be a thing, doesn't it? So the stratosphere is the second layer of Earth's atmosphere. It runs from the tropopause at 10 kilometers up to about 50 kilometers. So again, all these things, when we talk about the levels and where they start and where they stop, vary based on weather and based on specifically temperature. Because there's a reason that we divide the levels of the atmosphere up into temperature, or excuse me, in the layers by themselves. And we're going to hit on that reason right here. So the stratosphere is defined as the portion of the atmosphere where the temperature starts to increase. So in the troposphere, where we live most of the part, as you go higher, it gets colder. That's why when you go up the top of a mountain, it's got snow on it, especially the big ones, because it's colder. But here's where it flips. When you hit the stratospheres, when you keep going up, it keeps getting colder and colder and colder. You're reading your thermometer, and then suddenly when the thermometer starts going back the other way, you now know you're in the stratosphere. It doesn't really matter what the altitude is when that temperature starts going back up, you've entered the stratosphere. The increase in temperature is mainly from gaseous contents of the layer, which is where the majority of the ozone resides. The ozone layer, you guys have heard of ozone, is a layer of ozone is a type of oxygen. It is a charged molecule, but it absorbs energy from the sun in the ultraviolet wavelength. We've heard of ultraviolet because UVA, UVB, when you put on suntan lotion, that's what you're protecting yourself against. So the ozone layer absorbs a lot of that energy. And by absorbing this energy, and again, remember what temperature is. Temperature is just a measure of the average kinetic energy of the molecule. So if these molecules of gas are absorbing energy, guess what they're going to do? Their temperature is going to go up. That's how we read that energy. So this is this absorption that causes the increase in temperature from minus 60 degrees centigrade, Celsius, at the tropopause to near zero. So it goes from minus 60 to zero. So is it really getting warm? No, not really. But it is warmer than that at the top of the stratosphere. So at the stratopause, it's back down to near zero. So the stratosphere is where passenger airliners, commercial jets, you routinely climb to the bottom of the stratosphere to get above weather, and they burn less fuel up there because their engines operate more efficiently. They want to get as high as they can, as fast as they can. Number one, to get over weather. Number two, because their engines operate more efficiently up in that atmosphere. And there's less resistance as you go, because again, all the air molecules are down here in the troposphere. There's fewer and fewer and fewer. You go farther up. That's why the air pressure goes down. Here's the stratosphere. It goes from 10. Well, this thing says 48, but again, it's 10 to just 50. Remember 50. is the stratosphere. This thing, here's the ozone layer, just right in here. So that's what that is. The next layer up after the stratopause, there's one of those words, we got to know what they are. We run into the mesosphere. Occupying the space from 50 to 80 kilometers, the mesosphere has the coldest recorded temperatures on Earth. So again, here's why we've divided this into layers, because of temperature change. So when you go in after the stratopause, you go in the mesosphere, and the temperature starts going back down. So between, when you hit 0 degrees Celsius at the top of the the stratopause, and the temperature starts going back down. So when you climb up in the mesosphere, it drops to minus 85 degrees at the mesopause. Oh, look at that. It just keeps on going with the same nomenclature. Minus 85 degrees. The only human vehicles that regularly reach this layer are rocket powered. So sounding rockets, rocket powered aircraft. There's no real weather in this layer, but on occasion, some water vapor sneaks up this high. When it forms noctilucent clouds. There's a word you probably want to keep an eye on, noctilucent. Here's a picture of noctilucent clouds. The only time you ever see these things are during astronomical twilight. So the sun's already gone down over the horizon and is now shining upwards behind these things and illuminating them from beneath. When the sun's above them, you can't see them because they're how thin and how wispy they are. Only when it gets the sun goes down below the horizon and is shining up behind them, excuse me, do you get to be able to see them. But they're called noctilucent clouds. Those are the highest clouds that form in the atmosphere that we know about. So the top edge of the mesosphere is the mesopause. There again. So go back up here. So it says mesosphere. Again, it's a fairly small layer from 50 to 80. And we get into a big layer called the thermosphere. The next layer is the thermosphere. The thermosphere runs from 80 kilometers to 500 to 1,000 kilometers up. Wow, that's a huge difference, and it's a huge variation there, isn't it? That's 500 kilometers difference depending on what. Here we go. So there's a large variation where it ends that relies on solar activity. Solar activity means what? The sun. So the top end of the thermosphere basically relies on what's going on the sun. Like, wait a minute, now we're not talking about things that happen on the Earth that make an effect. This is what's happening with the sun has this kind of effect on our planet. 500 to 1,000 kilometers. That's a huge difference in where this edge of this thing is. So from the 80 to the 550 kilometers is also known as the ionosphere. So the ionosphere is where the electromagnetic energy from the sun interacts with gas molecules that exist up that high. The energy energy from the sun causes the electrons to peel off their atoms, creating ions. That's the word ionosphere. In the ionosphere, in the thermosphere, the temperature starts to increase as you go higher. So it goes down in the first level, it goes up in the second, it goes down in the third, now it goes back up in the fourth. Starting at minus 85 at the mesopause, it climbs to as high as 1,500 degrees Celsius. Though as a human, we really can't sense that because temperature for us, requires molecules of that higher energy level. Temperature is, again, a measure of kinetic energy in a molecule, how much it's vibrating effectively or how much it's moving. But again, there's not enough molecules of gas in that portion of the atmosphere to impart that kind of information to us if we happen to stick our hand out without any clothing on it. Because there's just so few molecules. Eventually, what actually ends up happening is we end up getting cooked by radiation because that's very high temperature, but we don't feel it. We just get cooked. It's kind of weird. So, but again, thermosphere. There's the name of it. The ionosphere is a portion of the thermosphere That's where a bunch of charged particles that help us, keep shielded from, the energy from the sun. And that's where, if you ever heard of aurora borealis, that's kicking up. And it starts at minus 85 degrees Celsius and climbs as high as 1500 degrees Celsius, which is extremely high temperature. But again, we would have a hard time feeling it, like with our skin, which is how humans sense temperature, because there's not enough gas molecules to impart that information to us. Now, 80 kilometers up to 480, 500 is the bottom of the normal thermosphere, but again, also can extend up north further than that to 1,000 kilometers. In the thermosphere is where things orbit. Space shuttle orbits in here. Your international satellite. Well, of course, you guys know we don't have space shuttle anymore, but the X-47. The Air Force's secret winged craft orbits in here. The satellites orbit the Earth in this range. The International Space Station is in this range. So I mean, effectively, it's kind of space, but not 100% space yet. But for all intents and purposes, if you're going up in a rocket, it's space. But in reality, it's still part of our atmosphere. And the last layer we see here is starts at the exobase. So again, here's where this kind of thing. So there's thermosphere, and if we follow the thing, it would be a thermopause, right? Well, unfortunately, science always has to create an exception for itself. And here it is for this one. So here's the exobase, which is the dividing line between the thermosphere and the next level, which is the exosphere. And it starts at the exobase, and we get the exosphere. So now the exosphere is interesting, but it says, as we said earlier, the exobase can vary due to solar activity anywhere from 500 to 1,000 kilometers at the bottom. The outer edge of the exosphere is at 10,000 kilometers. Like, wait a minute, that's way high. Well, yeah, 10,000 kilometers, way high. The boundary is fairly consistent and defined by the transition in from the particles of, that we see as Earth origin particles into the solar wind, which is the stream of charged particles released from the outer corona of the sun. Now, here's this picture. So right here in the middle is the Earth. And so remember, Earth's traveling through space. And just like a boat that travels through water, if you see the boat travels through water, it's got waves that kind of come off the front of it, and they call it the bow wave. Well, guess what? We have a bow wave moving through space here with the Earth. And it's you see right here, they call it the bow shock. So here's the Earth. And then here comes the solar wind flowing around, our atmosphere. And you have these things called the Van Allen radiation belts. We're not going to worry about too much of that. But again, where you stop running into Earth particles and start running into solar wind particles, which these red lines right here these are the solar winds right here. The yellow comes in, it kind of gets pocketed right here and blocked up. That's why I have these Van Allen radiation belts. And so solar wind goes around us as, our pocket of atmosphere here. Earth's atmosphere, 0 to 100 kilometers with the basic one. But then 10,000 kilometers is out here where this boundary is, where the solar wind is going around us. Crazy, yeah. But I mean, that's the boundary. So the exosphere boundary is 10,000 kilometers. And the reason the boundary, we can tell there's a boundary there, is because when we shift from particles from Earth's atmosphere to particles from the solar wind. Just kind of take that as it. So the outer boundary of the exosphere is where we shift from Earth particles Earth particles, Earth atmosphere particles. Solar wind particles. Easiest way to put that. So, exosphere, and effectively, again, I mean, stuff's orbiting the Earth at a lower levels than this. So, I mean, that's, technically, the science, so we call that space, but it's Earth space, not solar space. So here's again. So now this kind of tells you how things happen as we go up. So over here you see the air pressure. Air pressure starts down here at ground level, and we're just under 1,000 millibars, and drops and drops. Here's the temperature, drops from degrees Celsius down to the tropopause. It starts wandering back up and it hits the stratopause, wanders back down. Here's the coldest place on the planet, right here. We're at the mesopause. And then as we start climbing higher in the thermosphere, the temperature starts climbing back up again. So that's why we have the layers that we do. And that's why we give the boundaries that we do, is because it's based on the temperatures. Over here is pressure. Pressure starts at ground level, hits the tropopause, still has enough pressure to read. But once you get right here, it basically effectively becomes zero. 50 kilometers at the stratopause, it's 0.1%. And then at 90 kilometers, 0.0001%. So effectively, I mean, your instrumentation has to be amazingly, correct to be able to read 0.0001% air pressure. When you get up into the thermosphere, the air molecules can literally travel for kilometers before they run into each other. That's how few of them there are up there. Hope you guys enjoyed this, but again, review: troposphere, tropopause, stratosphere, stratopause, mesosphere, mesopause, thermosphere, ionosphere, exobase, exosphere, and when we get out of that, we're in the solar wind. Any questions? Please drop them into the Google Classroom. Remember to subscribe to the channel. Remember to like this video, and remember to say hi down in the comments. That counts as your attendance in class today. So, once again, from the Brenna Bunker, we wish you the best of the rest of your day, however long it may be. We'll see you tomorrow.